This is AQA A-level chemistry and the kinetics topic. This is part one of 6 videos in this particular topic, and it builds on the work that you've done at GCSE on rates of reaction. So as always, I'm going to recommend that you pause the video as you go, try the activities and see how you do. Going to start off by looking back at GCSE and looking at collision theory. So we need to know the principles of collision theory. There's a little tip here that's going to be important for later on within this topic about the impact of increasing temperature on the rate of reaction. But as a first task, have a think about what collision theory means to you from your knowledge of GCSE chemistry. And hopefully you're remembering that the particles must collide to react. They can't react unless they have that contact. But actually only a very small number of collisions result in a reaction. The vast majority of them will bounce off each other or slide past each other, and the collision does not result in a reaction. So for a reaction to occur, the key point here is that they collide with sufficient energy for that collision to result in a reaction. And specifically, that means they need to collide with energy equal to or greater than the activation energy. So let's take a look at this. How would you go about describing and explaining the shape of this graph? Well, we've got the definition here. Activation energy, the minimum energy required for a collision to result in a reaction. Nice and straightforward, important that we remember. But what do we see within this graph? Well, we can see that the volume of H2 is going up, but it increases fastest at the start at T is 0 seconds, and it slows down over time. So it slows over time, the rate we're producing hydrogen less quickly, and eventually the rate will decrease to 0. The reaction eventually stops. So from this very simple question, gone straight to the answer, we know that hydrogen is a product here, and we know that because the volume of it has gone up over time. A reactant graph would be a downward curve, eventually reaching a straight line, potentially at 0 if it's a limiting reagent, but maybe higher if it's in excess. With that in mind, have a think about this question. So we're actually told in the reaction that 1A reacts with 2Bs to make 1 mole of C. What does the graph show us about the amounts of A, B and C? Well, it's difficult to quantify unless you're actually measuring gradients, but A and B here are the reactants. We know that because the curves are downward, and we know that B is the limiting reagent. We know that because we run out of B and there is still A left over. So the A is very much in excess. You can also see, and it could be interesting to point out, that the B decreases much more sharply at the beginning than A does. And when you see that A is reacting with 2B, that does make sense that the B is getting used up more quickly. Okay, we're going to move on to another activity here to get us thinking about correct keywords, explaining what we mean when we talk about things being dilute or concentrated. So this is the more dilute one that I've labelled, and this is the more concentrated. It's not enough to say that there are more particles in a concentrated solution. You must say there are more molecules or particles in a set volume or fixed volume. This has been done in 2 dimensions. The area of these 2 squares is the same. We would be dealing with this in 3 dimensions. So there are more molecules in this volume than there are here. That makes it more concentrated. Moving on again, a few questions to you to think about here. Pause, have a read through and see how you do. So in the first question, we're asking what happens to the concentration of products over time? Well, the concentration of products, and we can see that here, but we know that it increases. We can see that from the graph, but it isn't just that it increases. The rate of increase does slow down over time, and eventually it comes to a rate of 0. It stops. We don't make any more. Now for question number 2, when and why is the rate in any reaction fastest? Well, you can see the steepest portion of the line is at the beginning. So it's when t is 0 seconds. And that's because there are more reactants available. There are more reacting particles, which means there are more collisions. And it makes sense from collision theory that if there are more collisions, there will be more successful collisions, and therefore the rate of reaction will be higher. And as we use up the reactants, and this is going on to question 3 now, the reactants are used up over time, and that means there are fewer collisions. And if there are fewer collisions, that means there are fewer successful collisions, which means the rate begins to slow. So what is the actual rate definition for rate of reaction? Well, it's already hinted at actually, and number 5 alludes to this as well. So the rate of change of concentration, the square brackets mean concentration in moles per decimeter cubed. The rate of change of concentration of products or negative rate of change of reactants over change in time. So rate of change of concentration of products and reactants over time. And rather than answer question 5, I'm going to go to the units here. So the rate of concentration, or the units for concentration, are mole dm to the minus 3. And we're dividing that by seconds. So in standard form, that becomes s to the minus 1. Okay, we're going to finish off this video by looking at how pressure affects rate of reaction. And if we think about pressure, we're thinking about similar to concentration, but with gases. And I could talk about having more particles in a given volume. I'm actually going to quantify this one. Let's imagine that we double the pressure. If we double the pressure, we are doubling the number of collisions because we're doubling the number of particles in that volume. And if we double the number of collisions, we're going to double the number of successful collisions, those where there is energy equal to or greater than the activation energy. And that means that we double the rate. And we've got this quantifiable link through. We double, 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 double. Now, what's really important, we didn't specify this on concentration, but that is actually true when we consider pressure, concentration, and surface area. However, it is not true for temperature, as was discussed at the start of this video, and as will be discussed in a later video. Now that brings us to the end of part 1 of the kinetics topic. Thank you for listening, and goodbye.